All right, welcome to the second part of our static and dynamic analysis of this mechanism. Um, we left off where we left off in class, actually, on Tuesday. We're going to continue by expressing the third and fourth equations in the world frame. So for that purpose, let's start with equation 3. When I inspect equation 3 here, I copied them down here for convenience. When I look at equation 3 right there, I see that I have an F12. I've already accounted for that. I can immediately account for the gravitational forcing, of course, but I still don't, at least, I still have to express the acceleration of the center of mass of the second rigid body in terms of the variables theta 1, theta 2, theta 1 dot, theta 2 dot, theta 2 1 double dot, theta 2 double dot. Yeah, that I need to do that. So that's going to be a bit longer than the acceleration of c1 because I have to go through the first link to get to the second link's center of mass, of course. So let's just start without further ado. My purpose here is to express acceleration of c2 in 0. So that, as you know, by definition is the derivative in the zeroth frame of the velocity of c2 in the zeroth frame. And that's by definition, of course, the derivative of a vector that goes from a point fixed in the world frame to the point c2. I can generate that point, that vector I should say, by first going from the origin of the world frame to point A, and then add to it a vector that goes from the point A to the point C2. This vector now is a position vector that goes from the origin of the world frame to C2. This is clearly, the point O is clearly a point fixed in the world frame, and this is the point of interest whose velocity and acceleration we want to find. So definitely we are satisfying the definition of velocity and acceleration here. Okay, so we have almost found the derivative of this. Essentially we found the derivative of half of that vector. So if we just multiply that, what we found, by 2, we'll find the derivative of this guy. And that's what I'm talking about is right over here. Where is it? It is right here. This is half of the derivative of the position vector that goes from point O to point A. Yeah. So let me continue over here on the, let's just see. Let me continue over here. I'll take that out and I write what I have over there. Actually, let me just copy that. Undo, copy, paste, and I don't need that divided by 2 actually, so I just have a1 times that. This is, of course, a double derivative of ROA. Yeah, what I need to add is over here, what I need to add is the double derivative of RA to C2. Yeah, that's what I need to add. Okay, so let's try and do that. I'll actually go to the next line, add to it derivative in 0 of RAC2, and this is equal to, so RAC2, let me write over here, RAC2 is what? It's equal to A2 over 2 in, if we have a coordinate system that points such that x2 points along the midline of the second link, I would say this is x2, yeah? But then I would express x2 in the zeroth frame, and this would come out to be what exactly? It's going to come out to be A2 over 2 sine of 1, 2 minus cosine of 1, 2. Okay, this is expressed in the zeroth frame now. Okay, so going back to this here, I have a1 theta 1 double dot cosine 1 sine 1 0 plus a1 theta 1 dot squared minus sine 1 cosine 1 0 plus d dt in 0 of a2 over 2. Now the derivative of the vector right there, right? Since this is expressed in the zeroth frame, now I can just go ahead and differentiate the coordinates here, components, which gives me theta 1 dot plus theta 2 dot, my cosine 1 2, and then here sine 1 2. Yeah. And finally, I need to take another derivative of that expression. Yeah. So this is going to be a1 theta 1 double dot cosine 1 sine 1 0 plus a1 theta 1 dot squared minus sine 1 cosine 1 0 plus a2 over 2 theta 1 double dot plus theta 2 double dot cosine 1 2 sine 1 2 0 plus a2 over 2 theta 1 dot plus theta 2 dot squared times minus sine 1 2 and what else, cosine 1 2 and 0. Yeah, that's what we get. Okay, so that's the acceleration of the point C2 written in terms of theta 1 dot, theta 1 double dot, theta 2 dot, and theta 2 double dot. Yeah, it's a pretty long expression, of course. Now we need to move this all the way back over here and insert it right there. Yeah, so to write equation 3 in terms of coordinates, I just go ahead and jot down all the components. So f12 we said was f12x, f12y, 0. Gravitational acceleration, gravitational forcing is m2 times 0 minus g0. And then finally m2 times the acceleration, which is all this thing. Yeah, so I'm just going to let's see, that's a pretty long expression to write here, so I'm just going to refer to it, keep referring to it as that. But whenever you see that now, keep in mind that I mean this expression right there. Okay, so that's we have to live with that. I'm sorry about that. And we assume everything over there here is expressed in the zeroth frame, as are these guys, right? They're all expressed in the zeroth frame. Okay, so that's the third equation. Of course, you know, substitute this whole expression for this whenever you need to write it in matrix form. Yeah. And finally, equation 4. Let me copy that again once more so that I can work on it over here. Okay, so the vector that goes from C2 to A is of course equal to negative of this vector right there. Yeah, and that vector we found out was this, so this is equal to minus a2 over 2 sine 1 2 minus cosine 1 2 and 0. Hence I have RC2A cross F12. What does that look like? Well, it looks like 0 0, yeah, and then this cross F12, which gives you what? Let's see, just move this over here so I can put minus a2 over 2 here. and add s1 to f1 to y plus cosine 1 to f1 to x. Yeah, that's it. So, and we know that the angular acceleration of the second frame in the zeroth frame is equal to theta 1 double dot plus theta 2 double dot in the z0 direction. Yeah, so I can just go ahead and write these equations now. It looks like the first term, the cross product term, looks like minus a2 over 2 0 0 sine 1 to f1 to y plus cosine 1 to f1 to x plus m2, plus 0 0 tau 2 minus this moment of inertia, the second rigid body, times 0 0 theta 1 double dot plus theta 2 double dot equals 0. Okay, so that completes our discussion of the equations of motion. So to be, complete, equation 1 here, equation 2 here, equation 3 here, with this, of course, yeah, and then equation 4 right here constitute the equations of motion. Yeah, this is 4. Now we want to put this into a matrix times unknowns equals unknowns form, so that we can just solve it using linear algebra, right? Now how do we do that? Well, our unknowns, our unknown vector, right, our unknown vector would consist of f01x, f01y, f12x, oops, I can't write it, x, f12y, theta 1 double dot, and theta 2 double dot transpose. That's our unknown vector, right? Now, so in order to write this, I might want to turn my screen here because otherwise it might not fit. So what I need to find is a matrix, a 6 by 6 matrix, times this unknown vector. Let's call this unknown vector, let's call this unknown vector capital X, okay, equals this capital X vector will come here, equals some known vector B. Yeah, that's what I want to do. Okay, so how do I do that? Since this may not fit, I'm going to be a bit more clever, and I'm first going to populate this matrix, and depending on it, how long it takes, I'm going to move this back and forth. Okay, actually let's just write that vector x as well, since I can move it. I couldn't move it on the board, but I can move it digitally here, so much more power. So I'm gonna write this out. Great. Okay, so in order to write this out, the first equation will correspond to the first equation in I. The second equation will correspond to the second row will correspond to the second equation in I. Third row will correspond to the equation, the only non-trivial equation in double I. The fourth row will correspond to the first equation in triple I. The fifth row is going to correspond to the second equation in triple I, and the last row is going to correspond to this only non-trivial equation in IV. Okay. Okay, so let's start with the first equation. What I need is go back over here, all the way over here, and read off the component of f01x, f01y, f12x, f12y, etc. So since it's going to be difficult for me to go back and forth, I'm going to try to copy this temporarily down there and work over there, okay? So copy. Okay, so now we're working on this equation right here. So what is the component of f01x in this equation? In the first equation, when I say the first equation, I'm talking about this guy right here, right? This whole equation, whole thing being equal to 0, that's what I'm talking about. The component of f01x there is what? 1. So I'm going to put a 1 here. The component of f01y is 0, so let me put a 0 there. The component of f12x is -1. The component of f12y is 0. The component of, let's see, theta 1 double dot is what? It's over here, so that looks like minus 1 over 2 m1 a1 cosine 1. Yeah, that's what it looks like. And the component of theta 2 double dot is 0. Maybe I can center it a little bit here. So yeah, and this is the first equation. In terms of the unknowns. I still have to write. I still have. Let's see, this part of the first equation remaining. This one here, that's going to go to the right hand side. So I'm waiting on that for now. Okay, I'm just writing into this matrix what are the coefficients of these unknowns in the relevant equation. Okay. Okay, so now the second, I'm looking at the second equation here, the second equation, and I'm looking at the components or the coefficients of the unknowns in that equation. What is the coefficient of f01x there? It is 0, right? So put a 0 here. What's the coefficient of f01y? 1. What's the coefficient of f12x? 0. What's the coefficient of f12y? -1. The coefficient of f theta 1 double dot? Well, it is minus 1 over 2 m1 a1 s1, and then the coefficient of theta 2 double dot is 0. And we'll have to copy this back again when we start writing the known vector, because I've run out of space here. So for now we're done with it. We'll come back to it to write the known vector. Okay, now we're going to the double I equation. So let me copy that down there. Okay. What is the coefficient of f01x? Let's see. The coefficient of f01x here is minus a1 over 2 times c1. And this is already getting complicated. So let me move these over here a little bit. Move these over here. Move them a little bit over here. Move this over here. Okay. The coefficient of f01x is minus a1 over 2 times cosine of theta 1. So that's where we left off. The coefficient of f01y is, again, minus a1 over 2, but now multiplied by sine of theta 1, right? What is the coefficient of f12x? That's minus a1 over 2 cosine of theta 1. And the coefficient of f12y is minus a1 over 2 sine of theta 1. The coefficient of theta 1 double dot, right, is what? It's just minus I1. Yeah. In this case, it turns out to be that, and the coefficient of theta 2 double dot is 0. This was equation number 2. And we got equation number 2 by looking at this equation here. And yes. Okay, it looks good. Of course, I have the torque. It's going to go onto the right hand side, so I'm waiting on that for now. All right, so let's erase this and bring here the third equation. I'm going to bring this whole thing because I need that to know about the acceleration. Okay, so remember, this was the acceleration of C2 in 0. Yep. Okay, what is the coefficient of f01x? Well, it is 0, right? Is it? Yeah, it is. So 0. What's the coefficient of f01y? Also 0. Coefficient of f12x, it's just 1. Coefficient of f21 is 0. Coefficient of theta 1 double dot. So now I'm looking at this over here, right? Okay, theta 1 double dot term comes from here as well as here. Yeah, so I'm looking at those two terms, and what I see is the coefficient is minus m2 in minus m2 parentheses, right? A1 times cosine of theta 1 plus A2 over 2 times cosine 1, 2. Yeah? And the coefficient of theta 2 double dot, that only comes from this term here. So I'm looking at that. I have minus m2 times A2 over 2 cosine 1, 2. Yeah? That's great. Okay, now let's look at the second equation in here, the second equation, and write it as the fifth row over here. Okay, what is the coefficient of f01x and f01y? Those are both zeros. Coefficient of f12x is 0, f12y is 1. The coefficient of theta 1 double dot, again, comes from this term here and that term there. Yeah, it looks like it is equal to minus m2 a1 sine of theta 1 plus a2 over 2 sine theta 1 plus theta 2, and the coefficient of theta 2 double dot in that second equation over here is coming from this term, and it looks like that is minus m2 a2 over 2 sine 1, 2. Yeah. Okay, so we're done with this equation. Of course, modulo the known part, so we'll have to come back to get the known part out. And for the fourth equation, I already have the fourth equation above me, so I don't have to copy anything. And the fourth equation, the coefficient of f01x and f01y are both 0. The coefficient of f12x is minus a2 over 2 cosine theta 1 plus theta 2. Yeah. Coefficient of f12y is minus a2 over 2 sine 1, 2. Coefficient of theta 1 double dot is minus I2, and coefficient of theta 2 double dot is also minus I2. Okay, and what we have left to write here is the known vector B. To get the known vector, I'm gonna start copying again. So let's copy the first equation again and take the known part of it out. Copy. Okay, so what is the known part here? Well, this is a known vector and that is a known vector, right? I can take those parts out and write them over here as the first two components of the known vector. I might need to make the known vector a bit longer or taller. So let me try it again. Let's move this further down and let's make this a taller vector. Okay, the known vector consists of course, this one, but since it wants to go to the right hand side, I'm going to have to negate that, right? So it's going to be, well, the first component of it is 0, so I'm not going to write that. The first component of this is not 0, so I'm going to write that first. Looks like it's m1 a1 over 2 theta 1 dot squared and the minus s1, so sine of theta 1 but with a minus. Yeah. The second component does involve m1 times g and then a plus m1 a1 divided by 2 theta 1 dot squared cosine of 1. Yeah, and that's all the known parts in this equation here, and so I'm done with that. I can erase this part and bring in the second equation now, which is right here. Take this one, copy. Here the only known part is here, the torque that we're applying, right? So I can just put it on the right hand side and write that this is equal to negative tau 1. That's simple. That's pretty straightforward. Erasing this now and bringing in the third equation, which is right here. Okay, what are the knowns in this equation? There's quite a few of knowns here. This vector again is the gravity vector, which is known. Other stuff that are known are, this term is known, that term is known, right? Because it depends on the velocity and the position only. So having done the kinematics, we know those values. So I can go ahead and put them on the right hand side. Let's do it. The first equation tells me it looks like minus m2 a1 theta 1 dot squared sine of theta 1. I will need to move this a little bit to the left, to the right. Then I have minus m2 times a2 over 2 theta 1 dot plus theta 2 dot squared times sine of theta 1 plus theta 2. Yeah. Now looking at the second equation over here, to right over there, yeah, I have m2 times g plus m2 a1 theta 1 dot squared cosine of theta 1, and then plus m2 times a2 over 2 theta 1 dot plus theta 2 dot squared. So let me write them a little bit better. Theta 2 dot squared times cosine of theta 1 plus theta 2. Yeah. And those are all the knowns for this third equation, the triple I equation. So I'm going to get rid of this now, and finally pull in the fourth equation from here and work on moving the unknowns, the knowns into the matrix vector equation we're writing down. So the knowns here is, again, consists of only this vector, right? The other stuff are unknowns. So this is going to be just, when I put it on the right hand side, it just consists of minus tau 2. Okay. And finally we have our equations. Okay, here they are. I'm gonna try to stay here for a while. This whole matrix right here, we can call that matrix A. Okay, and we call this the vector of unknowns, so X, and this is the vector of knowns, call it P. And so we want to solve for the capital X here. Whatever you see in the vector B should be your knowns, right? And whatever you see in matrix A are the coefficients of the unknowns coming from those force and moment balance equations in dynamic form, of course, right? So the only thing we have left to do is go back all the way to the top, take these values, take these known values and plug them into our known vector B, right? And the known matrix A, evaluate them numerically, and then compute A inverse times B, which will give us our unknown vector X, right? So to finally finish this discussion off, I'm going to go all the way back down and say that what we've gotten here is an equation A times X equals B, where this and that are known numerically, right? So from here I can solve for X. In Julia or MATLAB, you would do A backslash B, which is theoretically is the same thing as A inverse B. Okay? And that finishes our discussion of this problem. I will go into Julia and plug in the values and tell you what the numerical values come out for these constants, for these unknowns here, not constants. And I'll just write those answers on our website, and I'm not going to make another video just to report the numerical values for these unknowns, but I'm just gonna, as I said, record them on the website. All right, thank you for listening.